Preview video 8.7, volume of spheres and similarity. Last one, folks. Ready? Inhale. Deep breath, hold. Slowly exhale. We're going to be coming back to this lovely illustration in just a moment. Spheres and similarity. Spheres and similarity. Before we do spheres and similarity, it's really important you take a moment and you understand your squares and your cubes. I want you to do as many of these as you can without a calculator. Okay, so all of the yellow you should be able to do without a calculator. And then hitting about right here, yes, you can use a calculator. So go ahead, fill all of those out. Pause the video and restart when you're done. Go. Alrighty, folks, you should be just about done with these. You really need to have these two columns memorized. So straight down, of course, that's 4, 9, 16, 25, 36, 49, 64, 81, and 100. 10 cubed. This is how you can kind of judge your cubes when you're trying to do guessing checks. 10 cubed is 10 times 10 times 10, which makes this 1,000. And then 2 times 2 times 2 is 8. So if you have a number between 8 and 1,000, your cube is under 10. That's just kind of the way to look at it. Of course, this is 3 times 3, which is 9 times 3, 27. 4 times 4, which is 16 times 4, again, 64. 5 times 5, which is 25, times 5 again, 125. 6 times 6, 36, times 6 again, 216. This is 343. And then 8 times 8 times another 8. That is, I think, 512. Yep. And then this one's 729. You really need to memorize these to be able to spot them, because cubes are a little bit more difficult to spot. So just keep in mind your bookends here. Today we're going to be talking about the volume and something called surface area of spheres. I've introduced a new term to you. It's called surface area. What is the difference between volume and surface area? Take a look at my tennis ball here. My tennis ball. If I wanted to calculate the amount of felt on the outside of this tennis ball, that is what we call surface area. If I want to find the amount of space inside the tennis ball, that's volume. Another way to look at it is if you have a wrapped gift, surface area is like wrapping paper. It's a measure of the outer area of the solid. Volume would be the space inside that gift box. It's the amount of stuff, air, inside. We're not going to study surface area in detail. You just need to know it as a concept, but you do need to know something called a net. A net is if I take a solid and I unwrap its wrapping paper. What would it look like? So, for example, if I had this triangular prism and I had to unfold it, you can see that it would be 2 triangles and 3 rectangles. So we unfold it, and this 8 by 3 is right here, unfolded. And then the 8 by 5 unfolded would be here. This back edge is the 8 by 4 unfolded. And then you have the 2 top and bottom triangles. This thing in the middle is called a net. So if I just wanted the edge length of something, just length, like the height of that, the 8, that's 1 dimension. If I want the area around the wrapping paper, that is 2 dimensions. If I wanted the volume inside, that is 3 dimensions. So nets are a 2-dimensional concept. I'm going to give you a little bit of practice doing nets. You need to be able to do this. So here we have a pentagonal prism and a cone. And we're going to flatten it out. I'm going to start with this bottom pentagon. There are several ways you can redraw these things. So this is only one way. There could be multiple ways of unfolding this, and it's all right. So this edge here, that's that 13 right there. That's the 8.9. And now I'm going to come around and you can see that we have 1, 2, 3, 4, 5 rectangles. If you were to unfold them. And those rectangles would be 13 and that would be 7. And then it doesn't matter which rectangle you attach to, but then attached to one of them, if you were to fold it, would be yet another pentagon. That would be your top. So this would be your net of that solid. It's the wrapping paper, if you will. Now, cone's a little bit harder to see, so I'm actually just going to do the cone right here. I'm going to flatten it out. So a cone, if I were to do this and flatten it, you can see it's basically a sector area.
Kylie, Henry.
So coming here,
Please meet your parents in the visitor lodge.
my net for this is going to be that sector area. And then you have a circular base just kind of attached where exactly doesn't really matter. So that would be the net of a cone. Your job now is to take a net and fold it back into a solid. So the easiest way to do this is pretend this star thing's in your hand and pretend you're folding it physically. You have 5 points and it's coming to a point, and you should see that that net back into a solid is a hexagonal pyramid. So it is a hexagonal base. We're going to draw it in 3D, so we're going to draw it kind of squishy. Shade it for you. It's your hexagonal base. And then you have 6, technically, triangles. 1, 2, it's going to be dashed 3, dashed 4, 5, and 6. So that's going from a net back into a solid. You're like, what does this look like? Well, if I fold the 2 circles, I have a top and the bottom, and then I wrap it around with one giant rectangle, and you have yourself a can, cylinder. So if I wrap that back up into a solid, what you're looking at is a cylinder. You try these on your own. Fold them back into a cylinder, back into a solid on your own. Pause the video. So let's see how you did if you fold them back. This first one here is a cone. So it should look something like this. And our diameter here would be 10, and our slant height is 16.8. This one is a triangular based prism. So it looks like this. And it has 3 flat pieces, which makes the rectangle. And this last one, you should have gotten a square-based pyramid. So those are called nets. Now there's a reason why, because nets is what is used to introduce the concept of surface area. And you need that for spheres. I love spheres. Spheres are so easy. There's 3 reasons I love spheres. One, they're easy to draw. 2, there's no lateral area. 3, you only need one single dimension to find anything for a sphere, and that is the radius. So how do we draw a sphere in geometry? I know those of you in art, you do all this lovely shading stuff. We don't even bother with it in geometry. We just draw ourselves a circle. We draw like an equator thing, solid front, dotted back to represent depth. And then that would be the center. And your radius, we usually draw that way. But keep in mind, the radius is in 3 dimensions, which technically the radius can go like this. It can go down to this edge. And everything I'm drawing, even though it doesn't look like it's the same length, it would be the same length because it's a sphere. Surface area is a two-dimensional concept. It's like wrapping paper. Volume is a three-dimensional concept. It's like the gift inside. I'm not going to tell you where these equations come from. I'm just going to illustrate them, and you're going to memorize them. But this is a surface area of a sphere, a little animation that you might find helpful. So if I unwrap a sphere, and unfold it at its circumference, and I move all that leftover area, so I'm just rearranging the area here so that it's something you're familiar with. That wrap around is going to be the circumference times 2 radii. So technically it's d by times 2r, but we're going to use 2 pi r. So once again, it is the circumference 2 pi r times 2r, and that gives us the surface area of the sphere, which is 4 pi r squared. That's like the amount of felt needed for the tennis ball. Volume of a sphere is 4 pi r cubed over 3. I'm not going to explain that. That takes a page and a half to explain. You're just going to have to brute force memorize it for now. But here's the surface area of a sphere, and the volume of a sphere start exactly the same way, 4 pi r. Here's how I remember it. Area is a two-dimensional concept, so it's r squared. Volume is a three-dimensional concept, so it's r cubed, but then divided by 3. You must memorize those. Let's do a couple problems together. Put your finger there. I'd really like you to finger track, put your finger right there, and read out loud with me. Ready? You make the sound. Go. So we're doing this in exact terms and approximate, both surface area and volume. Start by writing your equations. Our radius is 8, so we're going to bring it right over here. 4 pi 8 times 8. And that's going to be 64 times 8. 64 times 4 is 512. And pi inches squared. We'll do the approximation in just a moment. This one is going to be 4 pi 8 times 8 times 8. Whoops, led you astray. That isn't 64 times 8. That is 64 times 4, friends, times 4, not 8. Thought that sounded wrong. 64 times 4. 16, carry the 1. There it is. That sounds more like it. 256 pi. This one down here, we are going to go 8 times 8 times 8, which, if you memorized it, you wouldn't have to even get out a calculator. That was 512. 4 pi 512 over 3. And that's not divisible by 3, so we're simply going to do 4 times 512. So my exact answer here for the volume is 2048 pi over 3. Check units, inches cubed. We won't worry about the approximate right now. Then you have things where you have to work backwards. Work backwards. Put your finger right there. Read, lips moving, sound coming out of your lips, finger right there. Read. The So this time we have the volume. Let's write it down. Write down the volume equation right underneath it. And we're trying to find surface area. So this one we work backwards. Our volume equals this. So we're coming right here, 972 pi. The only thing we need for surface area is a single radius. We're going to solve for the radius. So watch what we do. Cross multiply. 972 times 3, and then we got a pi there. And we got a 4 and a pi and r cubed. Divide by 4 and divide by pi. Cancel. I'm going to go 972 divided by 4, get 243 times 3, we get 729. 729 equals r cubed. And you're like, how do I do cubes on a calculator? You don't. You have the 1 through 10 memorized. Because when you go back here, 729 is 9 cubed. So I know my cube root, put a little 3 there, cube root is going to be 9. Bring it over here, 9 squared, 4 pi. That's 81 times 4. So my surface area is 324 pi. Check for units. What kind of units have we gotten? Meters. Meters squared. All right, friends, this page you are doing completely on your own. Pause the video and then restart. Pause the video. Okay, students, take a look. If you look at this, it says 36 pi and 36 pi, and you're like, it's the same thing. No, it's not, because this is 36 pi miles squared. This is 36 pi miles cubed. That's not the same thing. That's like saying I have 10 $1 bills versus 10 $10 bills. Units is everything. Okay, now we have one last concept. This is literally the last new concept in all of geometry, and it's a revisit of how we ended the first semester. We ended the first semester with a unit on things that had the same shape but a different size. Remember that? Same shape, different size. We call that similarity. We are revisiting the concept of similarity, but just in solids now. Oh, that doesn't help. I apologize. Okay, you're still laughing in spite of the bang, so I guess we're good. So right here, just to recap what scare means. Scare, which is the concept of similarity. Scare means that you're going to have congruent angles, ratios, which are equal. Congruent angles, ratios equal. Similarity means congruent angles, ratios equal. Box the RE, this is kind of where all your work's going to be. The slang definition of similarity is similar solids have the same shape, they're just a different size, like small, medium, large boxes of candy. So how do we tell if something's similar? We check to see if the ratios are equal. So right here, we're going to check our ratios. 3, 15, reduce. It's 1 to 5. 8 to 40, reduce. 8 goes into 40 5 times, also 1 to 5. 5 to 25, reduce. Also 1 to 5. So my ratios are equal, they are similar, and my scale factor, working left to right, is 1 to 5. Scale factor, ratio of the sides, simplified. So this was a yes, they are similar. Let's try these guys. Edge to edge, 15, 25. 5 goes into both. Three goes into both there. Three goes into both there. So my one edge is 3 to 5, and then this is 3 to 4, 3 to 4. My ratios do not match, so it is not similar. I want you to determine if these are similar. You have 30 seconds. Go. 30 seconds. What are your thoughts?
I didn't get there yet.
Okay. What is it you're comparing?
The tilt.
You mean the 20?
Yeah.
Okay, 20 to 100 reduces to what?
2 to 25.
What goes into both 20 and 100?
It's 5 to 25.
A little bit more. What's the largest number possible that goes into both 20 and 100? 10. 10 goes into 20 how many times? 2. Got it. And 10 goes into 100 how many times?
5.
10 goes in 100.
Oh, 10 times.
10 times. So this is a 2 to 5 ratio.
Okay.
Does that make sense?
Yeah.
Okay. So I got 2 to 10 ratio. So here, my radius is 10. What's my radius over here?
50.
50. What goes into both?
10. So it'd be 1 to 5.
It would be 1 to 5. 1, 2, 5. And 2 to 10 actually reduces by one more.
5.
Well, yes, 1, 2,
1 to
5. So both of them are 1 to 5, 1 to 5, as long as you pair it. So we would say, yes, they are similar. The slang definition of similarity is things have the same shape, different size. All spheres are automatically similar because they're the same shape. They don't have any bases and heights or anything. All spheres are automatically similar. Now, when things are similar, something really interesting happens. Let's recap our concept of dimensions. Okay, if something's just length, GTH, that's one dimension. Something that has both length and width, which is concept of area, that's two dimensions. Something that has length, width, and height has three dimensions. That's what we would call volume. So just length, one dimension. Length, width, as if you were painting a wall, two dimensions. Length, width, height, start thinking solids. Volume, three dimensions. Here's the key concept with this. When you change your dimensions, you change your ratios. Here's one we've been emphasizing the entire year. 1 yard in the first dimension, 1 yard, is 3 feet. That's probably what you learned way back second or third grade. So here's your ratio, 1 yard to 3 feet. When you get in the second dimension, that is a yard by a yard. So a yard squared is 9 feet squared. Watch what happens. If I take 1, square it, 3, square it, I get 1 to 9. A yard cubed is a yard by a yard by a yard. So it's 3 this way, 3 this way. And then we're going back. I think now we're going into cubes. You ask yourself, how many cubes are there? Think layers. That bottom layer is 9 by 9. 9 by 9, 9 by 9. So that's 3 layers of 9 cubes. So my volume's 27 feet cubed. 1 to 27, which is 1 to the third dimension, 3 to the third dimension. Here's what's going on. My first dimension ratio is to the first. My second dimension and ratio, I square it. Third dimensional ratio, cube. When you change dimensions, you change ratios. Do a quick little demo here. We have a single edge cubed, and now we're going to double that edge. So if this is 1 unit, this is 2 units, what would this look like? What would happen? So we have basically hands-on. You can see what's going to happen here. My edge, my edge. So this is 1 unit, this is 2 units. So the question is, if I double the single edge, what happens to the area? What happens to the volume? So my edges, I want you to just take a guess there. If you double the edge length, what do you think is going to happen to the volume? Take a wild guess. What do you think is going to happen to the area and the volume? Just guess. If I double this edge, what happens to both of those? Just take a wild guess. Just guess.
Same.
That's fine. You're right. Same, same. All right. So now let's see what actually happens. In one dimension here, my ratio was 1 to 2. 1 unit, 2 units. So that was my first dimension. 1 to 2. We're going to call this X to Y. Surface area of the small surface area, that's 1 square, 2 square, 3 square, 4 square, 5 square, 6. So the surface area of my small is going to be 6 units squared. Surface area of my large, that's 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. That is 6 times 4. So we get 24 units squared. So the ratio of my surface areas is going to be 1 to 4. Which is, I basically take that X, whatever it is, and square it, and the Y, and I square it. That's my surface area. Volume. The volume of this is simply 1 cube, 1 physical cube. The volume here, you think physical cubes, it's made up of 1, 2, 3, 4, 5, 6, 7, 8 cubes total. So my volume is 1 unit cubed and 8 units cubed. My volume is 1 to 8. If you watch carefully, if I take the 1 and cube it, I get 1. If I take the 2 and cube it, I get the 8. So my ratios change with the dimension. We will do 2 examples. Taking a look here. Basic concept. These aren't hard. When you change dimensions, you change ratios. Says the ratio of the volumes, right above the word volumes, put 3D, of these spheres is 27 to 8. The radius of the smaller sphere, the radius is 8 centimeters. What is the volume of the larger sphere? Okay, so step 1, the ratio of the volumes is going to be larger to smaller, 27 to 8. This is like saying x cubed, y cubed. Now we work backwards. What would be x and y? Well, in this case, x would be 3, because 3 times 3 times 3 is 27. And our y is going to be 2, because 2 times 2 times 2 is 8. Ratio of our surface areas would be 3 squared, 9, 2 squared, 4. What are we given here? We are given the radius of the larger, the smaller, so the smaller volume (4 pi 8 cubed over 3). 8 cubed. You should know that one. That's 512. So in your calculator, you are doing 512 times 4. 48 pi over 3. Box that. That's your volume of the smaller. Now we're going to make a proportion. Small over large, small over large. Our smaller here ratio of the volumes, we're dealing with volume, so we use the volume. It's going to be 27 to 8. The actual volume here is 2048 pi over 3. We're trying to find this volume here. Cross multiply. Some of you are freaking out with that fraction there. Relax. Okay, our cross multiplication looks like this. I'm going to color code it. That's going to be 8 times 2048 over 3 pi equals 27 times an unknown. I'm going to times both sides by 1 over 27. So I get 8 times 2048 pi over 27 times 3, and that is going to be our unknown volume. So yes, you may get a calculator from here. You get approximately 202.3 pi for our units here. Centimeters cubed. These 3 problems, 1, 2, and 3, we're going to finish in class because I think this video has gotten long enough. So make sure you have that ready to go when we get back. 1, 2, 3, 4. Have that ready to go when we get back.